Good morning, ladies and gentlemen. My name is Chi Wu from EG. First of all, I would like to thank the organization committee for inviting me here to deliver a speech. The title of my talk today is The New Era of Compound Semiconductors, Opportunities and the Challenges. And in this presentation, I will also talk about the research status at EG. So this is the outline of my talk. First, let's talk about compound semiconductors. The mainstream semiconductor, silicon, germanium, they are not compound semiconductor. And traditionally, when we talk about compound semiconductors, people think about gallium arsenide, indium phosphide, and the silicon germanium. They are the material for like line-emitting diodes, high-speed electronics. But for the past 15, 20 years, there are new generation of compound semiconductor, gallium nitride and the silicon carbide. So those materials are good for line-emitting diodes, high-speed electronics, and also high power and high temperature electronics. If you look at the table at the bottom side here, for silicon, the bandgap is 1.1 electron volt. And for compound semiconductor, the traditional compound semiconductor, like a gallium arsenide and the indium phosphide, the bandgap also like a 1 point something electron volt. And although the gallium arsenide and the indium phosphide, they can deliver higher mobility, up to close to 10,000 cm squared per volt second. But because of their bandgap is relatively small, so the breakdown field here, if you look at the breakdown field here, it's relatively small. So if you want to make the high power electronics or high temperature electronics, you need to look for materials which have a larger bandgap. So silicon carbide and the gallium nitride is the best candidates. The silicon carbide, the bandgap is 3.2 electron volt, and the gallium nitride is 3.4 electron volt. So they can sustain much higher breakdown field. So that's why when we talk about power electronics, people always use gallium nitride and the silicon carbide. So now let's look at the market trend of this compound semiconductors. So this is the global trend of compound semiconductor. In this presentation, we will focus on gallium nitride and the silicon carbide. So the right-hand side here is the estimate growth of the gallium nitride and the silicon carbide, the power electronics, so-called power electronics. So if you know the estimated growth of the power electronics will be over $1 billion this year, 2021. So for the next few years, the compound annual growth rate is estimated about 20%. And the application include hybrid and the electric vehicle, power supplies, and the photovoltaics. So now let's look at the compound semiconductor industry in Taiwan. So in Taiwan, we already have silicon carbide and gallium nitride industry. But if you look at the supply chain, the silicon carbide supply chain actually is not fully established yet. So from the powder, substrate, epitaxy, device fabrication, chip design, assembly, and the systems, if you look at the supply chain, in each area, only very few companies working on each area. And the gallium nitride supply chain is relatively more populated because of the 5G, RF data, and the data center. They are the mainstream application for the gallium nitride supply chain. I will talk about gallium nitride in the later part of my presentation. So if you look at the supply chain from substrate, epitaxy, device fabrication, chip design, assembly, and the system, there are more companies working on gallium nitride area. So in compound semiconductor industry in Taiwan, silicon carbide supply chain is not that fully established. Gallium nitride is better. So as a research institute, for E3, so E3 is trying to help the Taiwan's industry to develop the compound semiconductor supply chain. So now I will talk about the E3's strengths and the plan on this field. So first I will talk about the silicon carbide power electronics. And for the last 5 or 10 minutes of my talk, I will also talk about the gallium nitride for the wireless or high frequency application. So let's talk about silicon carbide first. So this is the roadmap for power electronic. So the x-axis is the voltage, the y-axis is the current. So for the application below 800 volt, so the current power electronics such as silicon MOSFET, silicon IGBT, and the gallium nitride, probably enough for the relatively low voltage application, such as e-bike, the consumer electronic like an air conditioner, the e-scooter, and for higher current such as 48 volt, hybrid electric car. Now the silicon IGBT and gallium nitride probably enough for those applications. But if you want to go to higher voltage, the application for higher voltage beyond 800 volt, like a servo motor, and the EV car, electric bus, and eventually the new renewable energy power plant. So those applications, you probably need a high voltage power electronics beyond 1000 volt. So for the traditional power electronics like IGBT and the silicon MOSFET, probably cannot sustain the high voltage. So for the application beyond 1000 volt, so we need to use gallium nitride and silicon carbide, and eventually probably we'll have to go to like a gallium oxide. So we set our overall strategy at E3. So we try to integrate the supply chain to develop the proper application in Taiwan. So we will try to help or work with the industry, the local industry, to build up the material growth, device design, and the testing capability. This can provide valuable service to our local companies and promote collaboration in the supply chain. So the main items need to be developed. Now we will develop the ingot growth, especially on silicon carbide ingot growth, device design, equipment, and the material quality assessment. So following the guideline in the previous slides, so E3 will engage in several critical areas of semiconductor compound semiconductor power electronics. We will work on both silicon carbide and the gallium nitride, and the silicon carbide mainly for power electronics, and gallium nitride for high frequency and high power electronics. So we will set up a roadmap, and we will develop the following technologies. We will develop materials for power device and the module package. And then we will also work on the device design and the fabrication, and the module design, and also module design and the fabrication. And then we will have a facility for module reliability. We all know that reliability is a very important issue for power electronics. And we will set up an industrial service and collaboration. So we will start with the compound semiconductor material growth. So the current supply for silicon carbide epitaxial grade wafers in highly demand. And we all know that silicon carbide is one of the hardest material on earth. So it's very difficult to cut and polish. And because of its the melting point. So we need to have a high temperature and the specific condition for its ingot growth. And at each, our material and the chemical engineering laboratories will be working on these areas. So we'll start with the silicon carbide powder purification. And this we will work with the China Steel Company, the local company in Kaohsiung. And they have a very pure carbon source. So we will start with silicon carbide powder purification. And we will set up our equipment in material and the chemical engineering laboratories at E3 for silicon carbide ingot growth. And also for silicon carbide ingot process. And as I mentioned before, the silicon carbide, the hardness is probably one of the hardest material in the world. So it's quite difficult to slice and dice and polish. So we will set up the slice in the facility, and we probably will use laser to slice the silicon carbide. So we have a laser center at E3, and we are working on using laser to cut the silicon carbide ingot. And then we will also set up the facility for silicon carbide wafer lapping and the polishing. And we'll develop our own silicon carbide epitaxy and then the inspection. So we have to have some inspection tool to inspect the defect of the silicon carbide wafer. So our MCL, the material and the chemical engineering laboratories at E3, we're working on these areas. So in device and the module area, my laboratories, EOSL, we're working on the device and the module areas. So nowadays in electric vehicles, the power density now is around 13 kilowatt per liter. So in the next 5 years, it will increase to close to 100 kilowatts per liter. And then the battery system will also be upgraded to more than 800 volt in the near future. And then the next platform will be 1700 volt. So to work on this area, so it's good to start with 800 volt and all the way to 1700 volt and eventually 3300 volt. So to work on those areas, so the following innovation is needed. So we need to have a good device performance. The efficiency per area need to be increased. So we need to have a vertical structure of the device to kind of reduce the surface area. And we need to have a device which can sustain up to 1700 volt and eventually to 3300 volt. And we also need to work on the device yield. And we have to set up the key intellectual property. And one of the most important things is that we have to optimize the module packaging and the package circuitry design. So let's look at the module requirements for the power electronics. This is the US Department of Energy target for electric vehicles. So for electric vehicle, there are 4 important parts which need the power electronics: the EV motor, the DC-DC converter, the onboard charger, and the charging station. So for EV motor, the cost, the dollar per kilowatt, nowadays probably around $5 per kilowatt. In next 4 or 5 years, it has to reduce to about $3 per kilowatt. And the same trend for DC-DC converter and the onboard charger. And then the most important thing is the power density. So for the EV motor to have the power density need to be increased about 10 times in the next 5 years, from currently around 5.7 kilowatt per liter to about 50 kilowatt per liter. And in DC-DC converter and the onboard charger, the power density also need to be increased. So all this, we need to have a higher efficiency power electronics. So With that, our each target for device and the module is following. So for device targets, we'll start with the 1.7 kilovolt power device. We need to reduce the R by 25%. And for step 2, we need to build up our own power module. And we have to reduce the volume by 30%. And eventually, we have to deliver the products for the industry. And from inverter, DC-DC converter, onboard charger, and the DC charging station. All these areas, we are working with our local industry to deliver these products. So for the module targets, we have to extend our device R&D capability into the commercial product. We will use both gallium nitride and the silicon carbide power device to build a compatible module and suitable for electric vehicles. So our module target, as I mentioned in the previous slide, our module target for inverter is 100 kilowatt per liter. DC-DC converter, for DC-DC converter, our target is 4.6 kilowatt per liter. Increased by close 3 times, with our current results. And for the onboard charger, we need to increase from the nowadays 0.6 kilowatt per liter to 4.6 kilowatt per liter. And for DC charging station, which is probably a very good business in the future once the electric vehicle is more populated. So for the DC charging station, the current status is probably around 180 kilowatts. So our target is to provide 50 to 200 kilowatts DC charging station. So we'll combine our technology with our local industry, especially in southern Taiwan. In southern Taiwan, there are a lot of local industry which have very strong connection to the tier 1, the international tier 1 power, electronic supply chain. So we'll work with them to penetrate our EV product market. So our current status at E3 for silicon carbide module research, we have a silicon carbide PIM power integrated module assembly technology, which already successfully transferred to the domestic company and the targeting for mass production next years. We also provide the prototype 12 kilovolt servo motor driver, which show 50% reduction of power loss and the 20% of power saving for industrial application. We also develop a motor driver, which integrates silicon carbide PIM, as I mentioned before, and the control IC to enhance the overall performance. So our silicon carbide module, we already work with our local company to provide the servo motor driver and the full factory machine. And for the less power requirement, we also have a gallium nitride module, which have less power requirements for some application with less power requirement. We provide the embedded die packaging under development for both the silicon MOSFET and the gallium nitride eHEM devices. And we also provide the gallium nitride based bidirectional DC-DC converter. And we also have a 48 volts BSG motor driver and applying the power system in packaging, which we work with tier 1 automotive and the PCB players in local industry. So our gallium nitride module now can provide the industry as a DC-DC converter, and which can be used in 48 volts, the hybrid electric vehicle. So at E3, we will also combine our strength in the ICT, like an AI capability, with the power electronics. So we set up a very high accuracy AI design platform for power electronic development. So we combine our, the previous knowledge database at E3. So we already developed a 95% accuracy platform, which, when we design the power electronics. And those database including various parts in each module, like a case, molding, device, and the wire bonding. So with this high accuracy AI added design platform, we can design a more accurate and more reliable power electronics. So at E3, we also built up a pilot line for power module ODM. We can customize power module for ODM service. We have the pilot line, which include die attach, interconnect, and the modularization. So we can provide a small amount of a pilot production, and which can serve the local company or international company. So we also build up our own testing service. We already have an AQG 324 testing measurement service, so which can provide the electrical performance measurement and the reliability testing. So with all this service, we have the service or the research activity all the way from the device, module, testing, and the pilot line service. And next, I will switch gear to the high frequency. So we work on gallium nitride for beyond 5G applications. So the E3's effort on RF for high frequency application, we mainly choose gallium nitride as our material to work from. And if you look at the left-hand side here, now if you compare the compound semiconductor, gallium arsenide, silicon carbide, and the gallium nitride. Gallium arsenide is in red, the red line here. Gallium arsenide is more suitable for high frequency electronic because they are high electromobility. Silicon carbide, on the other hand, is more suitable for high power electronics because they are excellent thermal conductivities in the high breakdown voltage. But if you need a material or if you need electronics which can work on high frequency and also deliver power, like the power amplifier in the like a 5G or 6G baseband, gallium nitride probably is the best material which can both provide or both deliver both high voltage and high frequency. So if you look at the right-hand side here, so for the gallium arsenide, which can deliver very high frequency, but they because of the smaller band gap of the gallium arsenide, the gallium arsenide material is not good for deliver power. Silicon carbide is good for power device, but the color frequency is quite low, so it's not good for the high frequency application. So for the power amplifier for the 5G and the beyond 5G application, which need both power and the high frequency, gallium nitride probably is the best candidate, and that's where the E3 is working on. So this is the international benchmark for gallium nitride high frequency devices. So nowadays, like Intel 2 years ago in IEDM, they show the gallium nitride silicon, which can deliver the Fmax up to 300 gigahertz. So we already at E3, we set up a goal in the next few years. We need to deliver. We need to work on the high frequency device. We hope to deliver the HAM device or make the HAM device which can deliver the Fmax more than 400 gigahertz. And with that device, we can make the high frequency power amplifier for the 5G and the beyond applications. So for the high frequency application, we have in our program, we have 4 parts. First, we have an epitaxy fab. We'll work on the 8-inch epitaxy wafer directly on silicon. And we know now the industry have gallium nitride on silicon carbide for 4-inch and 6-inch. Also gallium nitride on silicon for 6-inch. And we at each we will work on gallium nitride on silicon epitaxial growth at 8-inch wafer. And at each we already work on epitaxy for many years, so we are quite experienced in the gallium nitride epitaxy. So we have an 8-inch wafer lab at E3. So we will use this 8-inch wafer epitaxy wafer to make the high frequency device on 8-inch wafer. So it's we will develop the CMOS compatible process with such as lithography, etch, thin film, anneal, which is the standard. All of them are standard CMOS compatible process. And as I mentioned before, we have a very good advanced packaging fab, and we will integrate the packaging and the antenna and all the electronic, the IC and the power electronics into the same packaging. So we are in the packaging side, we have both 8-inch and 12-inch wafer level process. And we also, in the past 3-4 years, we built up a very good state-of-the-art sub-terahertz lab testing system. Then we can test the antenna up to 170 gigahertz, and we can have a material measurement also all the way from a few gigahertz to 140 gigahertz. Those are essential lab testing equipment for the high frequency electronic development. So this is the E3's sub-terahertz lab. So in this lab, we can have a active and passive testing platform. As I mentioned, we can test the active and the passive device all the way to 110 or 170 gigahertz. And for the dielectric material characterization, we can test the high frequency material all the way from 1 gigahertz to 170 gigahertz. And we also have a very 2 state-of-the-art antenna chambers, and which can measure the antenna, the frequency and the waveform of the antenna. And we also have a plan to upgrade our high frequency measurement or testing lab from now is 100-something gigahertz to 300 gigahertz for our high frequency or sub-terahertz program for 5G and beyond 5G, 6G applications. Finally, is my conclusion. We all know the rise of new generation in 5G and the AOT era brings the demand for new device suitable for high power, high temperature, and the high speed environment. And the new generation compound semiconductor, gallium nitride and the silicon carbide are the best candidate for these applications. However, there are still many challenges remains in specific application. And at E3, we set up a program to try to overcome those challenges, try to develop technology related to material growth, device purification, and the module packaging. And we will also work with our local industry, especially for those industry in southern Taiwan, and to develop a program and to boost our next stage, the power electronic in southern Taiwan, and boost the next stage, the economic growth. With that, I thank you so much for your attention. Thank you.